Hello, my name is Nigel Griffiths. I work in the Advanced Technology Centre in the UK, part of IBM Europe. This is the second of 3 movies looking at common misunderstandings about power processors. In this one we're going to be looking at, are logical CPUs real? And what is SMT, simultaneous multi-threading? We'll actually look at the second question first. In the first movie we looked at the various components inside a PowerBasics processor. And here we can see a couple of the things like the level 2 cache and the 2 CPUs on the single chip. If we now look at an individual CPU, we'll find that the instruction set, the instructions that a CPU can perform, are broken up into several units, and the different units inside the CPU actually handle the different instructions. So we find that there's fixed point, is what we tend to know as integer mass, add 1 to a register, add 2 register together, or take away the number you first thought of sort of operations. Then there's floating point math, so that's what the high performance guys like when they're doing calculations. We have load and store operations, which are loading data from memory or putting it back into memory, storing it away again. We have compare and branch operations. They give us the if statements in our code. And with PowerBasics we actually have a new one called the decimal floating point. This allows us to do very high precision maths, typically used for calculating money. But each of these different processor units can actually operate at the same time independently if the CPU is given the right mix of instructions. We also find that some of them appear so often that we actually, inside the CPU, implement more than one processor unit to do the same thing. So we have 2 floating point, 2 fixed point, and 2 load and store operations. So that while we're doing maths on 2 registers, we could be loading from memory the next number we actually need to operate on, again to increase our concurrency. Now in this diagram we're trying to show you what happens with a traditional processor. On the left we have these columns. Each of these little squares or oblongs are different instructions for the different programs. We have 5 programs here running in different colour, and there's a run queue of 5, and we're going to run this first light blue application by taking its instructions. In the middle here we have, you can see FX0 and FX1. This is the fixed point 1 and 0. The 2 different processing units inside the CPU. And as we go from left to right, we're operating different processor cycles. So each clock cycle we're doing different things. If you can imagine, we're going to do this operations here, and the next clock cycle we'll do these here, and so on as we move left to right. In the first clock cycle, we actually find the instruction mix is just right, so we're actually doing some integer maths, we're doing a floating point maths, and we're doing a compare and branch. In the second one, we can do 2 operations. In the third one, we've got a wait here. We need data from memory, it's not in a register, so we have to wait for the cache to catch up and supply us the data. Then we do 2 more operations. Then we find that it's time to schedule off the light blue process and bring in the yellow process, but we have to save all the registers. That takes a clock cycle, and then we have to bring in the new registers for the new process. That takes a clock cycle, and then we're off and running the second process, the yellow process. Now we find in here, out of all the possible instructions that we could have completed in these clock cycles, there's an awful lot of white space in here. If only we could get the programs to provide us 2 integers, 2 floating points, 2 load and stores every single clock cycle, we could actually make the processor a lot busier than it currently is. So somebody in development decided, well, can't we run another process using these unused processor units? And that's what we have with SMT, simultaneous multi-threading. We're actually going to run a further thread of execution, or another process, at the same time on the same CPUs by using those processor units which aren't actually used. And we'll look at that on the next foil. Now in this example we're running 2 processes at the same time, the blue and the yellow. We still have a run queue of 5, but we're actually running 2 processes at the same time. And the yellow process here is using parts of the CPU where the blue process doesn't actually need it. If they both want to use the same processing unit at the same time, well, one of them will have to do it this clock cycle and one of them will have to wait for the next clock cycle. Now we can see on the third clock cycle here, when the blue process is in a wait state waiting for the memory, the yellow process has his data in registers, so he can carry on processing. In fact, he gets all of the processing units that are available at that point. Later on we decide that the blue process needs to stop and we're going to run now the red process. Again, when we're saving the registers for the blue process and bringing in the red process registers, the yellow process can actually carry on running on the CPU and he can use whatever processing units he actually wants to at that point. So now I hope you can see that comparing this to the previous slide, we're actually getting a lot more processing done. Where at every clock cycle we're getting almost twice as many units of work, instructions actually completed at one time. And this is what simultaneous multi-threading is all about. Now before we go on any further, I better explain that this diagram is for illustration purposes. If we have a highly busy threaded application like a very busy web server, or we have a database running lots of simultaneous SQL statements, or lots of users connected and running their applications, then we find in the Power 5 typically SMT gave us about a 30% improvement in throughput. And with Power 6, because of internal changes and the scheduling of the instructions, we actually get something like 40% improvement with SMT. So we have a single CPU here operating, but it's running 2 programs at the same time. Now, an operating system in the past was very happy to schedule one process onto the CPU, but now we need 2 processes on this one physical CPU. And the way we do that is we describe to the operating system that this physical CPU actually is running 2 logical CPUs. So this is what the logical CPU really means. It's asking the operating system to schedule more than one, in fact 2, processes at the same time to one physical CPU. We're now going to look through a series of commands to investigate the physical CPUs and the logical CPUs and what happens when we switch SMT on and off. Here we have a command that we're going to look at and look at the number of processors. So lsdev minus C processor. Now this is confusing for a completely different reason. Earlier this logical partition was running with 4 dedicated CPUs and it's now running with 2 dedicated CPUs. So although it lists 4, you'll see that 2 of them are actually available. The other ones are only known about because they were switched on earlier on. Now a number of commands can give us a false impression of what is actually going on in the machine. An example is if you run SAR and ask it to give us details of the CPUs, it gives us the impression here that there are 0, 1, 2, 3 CPUs. This line is the average of those running on the machine, and it gives the impression that there's 4 CPUs. There's a little clue up here where it says L CPU equals 4, so this is logical CPUs, but if you don't notice that, you can be left with the impression that you have 4 genuine CPUs. We can also use a command like my own tool nmon, and we look at the number of CPUs here. Again, these are logical CPUs, and we can see that there's a couple busy and a couple not used at the moment. It gives you the impression again that there's 4 CPUs. If we use Topaz, again at the top left here we have CPUs and we have 4 of them, and again that gives us the impression that we got 4 CPUs when we don't really. We can run a command like lparstat -i, And here we can see that we have dedicated CPUs and we have SMT switched on, this SMT at the end of the line. Now these are dedicated, so our entitlement is 2, so we have 2 CPUs allocated here, and we can see online CPUs is 2. We can do this, the maximum here is for doing a dynamic CPU add, and the same down here for 4 CPUs, we can go up to that. So there's some 4s in here, and again that can confuse people. They start thinking that they actually have 4 CPUs. So it's this line here that tells us that we have 2 CPUs and SMT is switched on. If we look at a command like mpstat, again, it looks like there's 4 CPUs on this system, doesn't there? 0, 2, 3. Very easy to get confused. And up here it's telling us again a little clue, these are logical 4 CPUs. Now if I run a tool like nmon and we're watching these 4 CPUs, logical CPUs of course, we can actually see the processes that I'm running. I'm running something in the background just to generate workload here, that they do bounce around along the logical CPUs, move around now and again. There's just 2 programs running, and we can see that sometimes it runs the 2 applications on the same CPU. This 2 and 3 is the same physical CPU, but it will try and move them to different CPUs, and that's an optimization that it's doing there. It's better to the 2 applications to actually run on 2 different CPUs. If they were using 2 logical CPUs on the same physical CPU, then sometimes they'd be competing for those processing units inside the CPU. So it prefers to separate them onto 2 physical CPUs if it has different physical CPUs for every application that's running. If we added more applications, of course, it would be forced to use all the logical CPUs to get the work done. Now let's go to this little window down here, and I run this command here. Well, let's just try it without options to start with. This is SMT control, SMT-CTL, and it's telling us that currently SMT is enabled, and processor 0 has 2 processors, logical processors bound to it, and physical processor 2 has 2 processors bound to it. Now we can use this command to switch SMT off, and if we do that, we'll notice that the nmon tool here, and Topaz would do the same, it actually switches us now to show us the 2 real CPUs, and they only have 1 logical CPU on each. So I've switched from apparently 4 CPUs to 2 CPUs, but we still haven't actually changed the CPUs we're using. We've just switched it out of SMT mode, and we're now using 1 logical processor on each physical processor. And we can switch that back on. The -M is the mode, and the -W is when, and we say we'll do it right now. We could do it at boot time as well. We can see the workload splitting out again. One final command to look at is mpstat -s, and if we run that, then we can see for a physical processor we can see the 2 logical CPUs connected to it, and the split of work between those 2 logical CPUs. So we can see in this case the first one is doing a lot of work and the second one doing some work. Another thing to note is that the 2 logical CPUs will always appear in the same logical partition. The physical CPU is allocated to a logical partition when we've got shared CPUs, and so both of the logical CPUs always appear together in the same logical partition. Okay, well I hope that's been useful. Are logical CPUs real? No, they are not. Very clever device to allow two threads to run at the same time, intermixed in the CPU. And what is SMT? A very clever piece of technology that gives us between 30 and 40% performance boost if we have enough threads of execution, enough programs running at the same time.